right, so we're diving into response to acoustic forcing of laminar coflow jet diffusion flames.
From Combustion Science and Technology.
Yeah, you shared this paper with me. And
yeah.
honestly, the title alone really caught my eye. You know, we're talking about sound waves and how they affect how flames behave.
Yeah.
It sounds almost like science fiction.
It does kind of sound that way, but the science behind it is very real, and it's got serious implications for a lot of things.
So break it down for me.
Okay.
We've all seen, you know, a candle flame flicker. What's the big deal about using sound to influence that?
Well, think about it this way, that natural flickering that you see is actually a form of instability driven by buoyancy.
Right.
Hot gases rise, create these swirling patterns called vortices, and that contributes to the flame's kind of unpredictable dance.
Right.
What this research explores is whether we can impose a different kind of order using sound waves.
Okay, I'm starting to see where this is going.
Oh, okay.
So how did they actually set up this experiment? Were they blasting heavy metal at these flames?
Not quite.
Okay.
They used something called a laminar coflow jet diffusion flame.
Okay.
Which basically means the fuel and air mix in a very controlled way.
Right.
And the setup allows them to isolate the effect of the sound waves on the flame without other factors muddying the waters. And they introduce these precisely controlled sound waves, which are called acoustic forcing, to the fuel supply.
So what happened when they hit the flame with these sound waves? Did it start, like, doing the wave?
Kinda, yeah. They observed that at specific frequencies and amplitudes of the sound waves, the flame's flickering actually synchronized with the sound.
Oh.
So you can imagine, like, the flame is pulsing to the beat.
Right.
They call this phenomenon lock-in.
Okay.
And what's even more interesting is they observed multiple harmonic regimes.
Hold on. Harmonic regimes. That sounds pretty technical. Can you unpack that a bit?
Sure. Imagine you have a bass frequency.
For your sound wave.
Okay.
In these harmonic regimes, the flame's response frequency was a multiple of that bass frequency.
Okay.
So you might have a sound wave at, say, 100 hertz.
Right.
And the flame could be flickering at 200 hertz or even 300 hertz.
So it's like the flame is choosing to dance to a different tempo based on the sound.
Exactly.
That's wild. But how did they actually observe all this? Were they just eyeballing it?
They used some sophisticated imaging techniques.
Okay.
Specifically, they employed Particle Imaging Velocimetry, or PIV, and Reactive Mie Scattering.
Wow.
Or RMS.
Okay.
PIV allows you to track the velocity of particles in the flow, giving you a detailed picture of the flame's movement.
Right.
RMS, on the other hand, helps visualize the reaction zone of the flame.
So with these techniques, they could actually see how the sound waves were sculpting the flame structure in real time.
Exactly.
That's amazing. This is where I start to see how understanding this type of control could be incredibly useful.
Yeah.
I imagine designing a combustion system is
pretty complex. Yeah. Being able to influence the flame in such a precise way could open up a lot of possibilities.
You're absolutely right. And that's precisely what makes this research so fascinating.
Yeah.
It's not just about the visual spectacle of a flame responding to sound, but about unlocking the potential for more efficient and cleaner combustion technologies.
Yeah, this is already so much more than I expected.
Yeah.
I'm hooked. What else did they discover in this acoustic symphony of fire?
Well, one of the most intriguing findings was the phenomenon of frequency doubling.
Okay, let's unpack that then.
Okay.
What is this frequency doubling all about, and why is it important?
All right, so remember how we talked about those harmonic regimes?
Right.
Where the flame flickers at a multiple of the sound frequency?
Yeah.
Frequency doubling is a specific example of that.
Okay. Where
the flame pulsates at twice the frequency of the sound wave hitting it.
Okay, so the flame is essentially responding in a higher octave.
Yeah.
But what's causing it to do that?
It all boils down to the interaction of forces within the flame. The sound waves create regions of high-velocity gradients, which stretch the flame at certain points.
Okay.
This stretching leads to the formation of smaller bulges between the larger ones, effectively doubling the flickering frequency.
It's amazing how something as seemingly simple as sound can create these intricate patterns in a flame.
Yeah.
It really highlights the complexity of fluid dynamics.
Absolutely. And this complexity is precisely why research like this is so valuable.
Yeah.
It gives us a deeper understanding of the hydrodynamic mechanisms that are at play.
Okay.
Not just in this specific scenario, but in other instability modes in flames as well.
Okay, so we've got this flame dancing to the tune of sound waves, sometimes even doubling the tempo.
Right.
But how does this actually translate into real-world applications?
Yeah.
We touched on this a bit earlier,
Yeah.
but I'd love to delve deeper.
You're right. We need to connect this back to the bigger picture.
Yeah.
One of the key takeaways from this study is its potential to improve computational models of flames. These models are essential tools for engineers who design combustion systems, for everything from power plants to aircraft engines.
So instead of just building a combustion chamber and hoping for the best, they can actually simulate how the flame will behave.
Precisely. And the more accurate these simulations are, the better we can optimize those systems for efficiency, stability, and reduced emissions.
Right.
The quantitative results from this study, like the specific frequencies and amplitudes at which lock-in and frequency doubling occur, can be directly fed into these models.
So it's like giving the models a cheat sheet based on real-world experimental data.
Exactly.
That makes a lot of sense. Are there other areas where this research could have a significant impact?
Absolutely. Think about control systems.
Okay.
Imagine a system that could detect the onset of instability in a flame
Right.
and then use precisely timed sound waves to suppress it.
Wow.
That's the kind of technology this research could enable.
That sounds incredibly futuristic, using sound waves to essentially fine-tune a combustion process in real time.
Yeah.
It's amazing to think how such a seemingly simple concept could lead to such sophisticated applications.
And it's not just about efficiency.
Right.
Active control systems like that could also play a crucial role in reducing emissions.
Okay.
By optimizing the combustion process, we can minimize the production of harmful pollutants.
This is really highlighting the interdisciplinary nature of this research. It's bridging the gap between fundamental physics and real-world engineering challenges.
Exactly. And that's what makes this field so exciting. It's at the intersection of multiple disciplines, and the potential for breakthroughs is immense.
This is already blowing my mind. But before we get too carried away with the possibilities, let's bring it back to the paper.
Okay.
Were there any other particularly striking findings that you think our listeners should know about?
Well, I think what strikes me most is how this research really sheds light on something we often take for granted,
Right.
a humble flame.
Yeah, it's easy to see a flickering candle and not think much of it.
Right.
But there's so much complexity beneath the surface.
Yeah, it's a testament to how much we still don't know
Right.
about even the most familiar phenomena. And this study really emphasizes the importance of fundamental research. You know, it's not always about immediate practical applications. Sometimes it's about deepening our understanding of,
Yeah.
the underlying principles that govern our world.
I'm also struck by how this research has implications far beyond just making flames dance to music.
Yeah,
We've talked about computational models and control systems,
right.
but I imagine the applications extend to other areas as well.
You're absolutely right.
Yeah.
For instance, understanding the dynamics of flame instability
Right?
can be crucial in fire safety research.
Oh.
Knowing how certain conditions might lead to more unstable and potentially dangerous flames
Yeah.
could help in designing better fire prevention and suppression systems.
It's a reminder that scientific discoveries often have a ripple effect, impacting fields we might not initially consider.
Precisely. And this research on acoustic forcing is just one piece of the puzzle. When it comes to understanding and controlling combustion,
Yeah.
there's still so much more to explore.
So where do you think this research goes from here? What are the next big questions that scientists will be tackling in this field?
Well, one area of active research is extending these findings
Yeah.
to more complex flame configurations.
Okay.
This study focused on laminar flames,
Right.
which are very controlled and stable. But in many real-world applications,
Right.
flames are turbulent
Yeah.
with much more chaotic flow patterns.
Yeah.
Understanding how acoustic forcing affects turbulent flames is a major challenge.
That makes sense. It sounds like there's a big step between controlling a flame in a lab setting
Right.
and applying those same principles to something like a jet engine.
It's a significant challenge,
Yeah.
but it's one that researchers are actively tackling.
Right.
And the insights gained from studying laminar flames provide a valuable foundation for understanding the more complex dynamics of turbulent combustion.
It's fascinating to think that we're still uncovering so much about something as fundamental as fire.
And that's the beauty of science.
Yeah.
It's a constant process of discovery, pushing the boundaries of our knowledge and understanding.
Well, I think we've done a pretty good job of unpacking this research paper.
We did.
Thanks for taking us on this deep dive.
Yeah.
It's been illuminating.
It's been my pleasure. Always happy to delve into the fascinating world of combustion.